Hello everyone, welcome to Viterbi Bros, and today's video we're gonna talk about searching algorithms. So in this video we're gonna discuss two classic searching algorithms that have been widely used in computer science and especially EE355. So the first searching algorithm is the linear search, and the second one gonna be the binary search. And it turned out that the binary search has a better searching performance than the linear one. And why is that? Let's figure it out together. So let's start with linear search. In order to understand how linear search works, let's have some example. You are given an unsorted list with 11 elements, and your job is to find the position of number 2. Number 2 is right here. And as a human being, when you see this list, you're gonna say, oh, number 2 is right here, because I just see it. So simple. And then after that, you're gonna count to get the position of number 2. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. But now, let's ask this question. Does the machine work the same thing? The answer is going to be no. Because the machine cannot see the image of this list and then conclude oh, number 2 is right here. And then counting until 8 quickly as human. Turn out that machine going to do a more safer way. You're going to scanning each element, like asking, are you number 2, are you number 2, are you number 2, until it's reached, and find number 2 at the 8th position. And after that, it's gonna return the position, which is 8. The scanning approach that we just did, it actually called a linear search. Linear in this case mean you going one direction and straight. So the scanning approach that we just did actually go into this direction. But the machine can also use in this direction as well, as long as a one direction and straight line. So now the question is, what is the runtime of this linear search? Once again, when we talk about the runtime, we always care about the worst case scenario. So the worst case scenario for this list or this problem is when number 2 is on the back of the list. So let's say number 2 is on the back of the list, which is right here. And because number 2 is on the back, the machine have to scanning exactly all the elements until it's reaching number 2. And since there are 11 elements in this list, it have to go exactly 11 times in order to reach number 2. So we can say that the runtime equal to the length of the list in the worst case scenario. So now let's wrap it up in more general way. And assume you don't know, so the length gonna be n. Therefore, the runtime of this list, when you want to searching for number 2 on the back of the list right here, the runtime gonna be on. And for the n function, when you grab it out, it's actually a linear function that's going straight in one direction. So that's why this is called a linear search due to the runtime on. So let's start with binary search and have some intuition about it. So for the binary search, the list has to be sorted. Unlike the linear search, where you can make the list either sorted or unsorted, but for the binary search, it has to be sorted in order to work. So let's assume we have a sorted list in the increasing order from 1 to 10, and your job is to find number 9, which is right here. And now let's say you're using linear search to searching for number 9. You're starting at position 1. Then it takes you at most 9 times in order to scanning to all these 9 elements and then find your number 9. So now what happens if you move your starting point to number 2? Then it takes you at most 8 times to search for number 9. Similarly, if you move to number 3, it takes you 7 times. So the conclusion is that the more you increase your starting point, the lesser the time you're gonna searching for your target. So now let's say I'm starting at number 7 and then I want to search for number 9. And since this is a sorted list, therefore number 9 is always on the right half of number 7. So it's gonna take at most 3 times to reach for number 9. And when you search for number 2, it's always on the left half of number 7, because 2 is less than 7, and it's take at most 6 times for you to scanning to all this to find for number 2. So let's have one scenario when your friend give you this sorted array and then he challenge you to find number 2, which is right here. And by some lucky and random moment, you find the starting point at number 3. It will take you at most 2 times to find a number that your friend wanted you to find, which is number 2. But now your friend, he changed his mind. He said, oh, I want to find number 9. And since your starting point is at number 3, it's gonna take you 7 times to find number 9. And if you move your starting point up to number 7, then it's gonna take you 3 times to find number 9. But if your friend, he want to find number 1 right here, it costs you 6 times to scanning for number 1. And we cannot keep playing this trial and error games because sometimes it may cost less time to scanning for something on the right, but can end up more times on the left. So the best way to optimize this is to pick the starting point in the middle. Therefore, your right hand and your left hand have equal chance to be searched. They all have equal number. So there won't be the case like, oh, your left is too fast and then your right is too slow. This time, both left and right gonna have equal amount of times they're gonna be searched. So after knowing some intuition about the Viterbi search, so now let's work through the real Viterbi search problems. At the beginning, we assume your list is sorted and in increasing order. So let's have some example. I've given you again the list of 10 elements that's from 1 to 10. And this time I give you another equation to find the middle starting point. So the middle starting point gonna equal to the summation of the high plus the low position, and you divide them by 2. So let's say number 1 right here is at position 0. Number 10 right here is at the position 9. So 9 plus 0 and you divide them by 2, you're gonna get 4.5. And 4.5 is kind of like right here. Therefore, 5 or 6 can be your middle starting point. So you can pick either one of them. So now, let's start with this problem. At the beginning, you're gonna find your middle starting point. And as we talked before, it's either 5 or 6. So I'm gonna pick 5 this time. And after you find your middle starting point, you're gonna follow this algorithms in order to perform Viterbi search. So you're gonna compare your middle starting point with the target or the number that you wanna search for. So let's say the target gonna be number 2. You wanna search for number 2, which is right here. So now you're gonna compare your middle starting point with your target. So 5 is greater than 2. And here's the thing. Since your list is in increasing order, so everything on the right side of your middle starting point on number 5 is always be greater than 5. Because it's in increasing order. And everything on the left side of number 5 always less than 5. Therefore, it doesn't make any sense for you to have number 2 on the right side because everything on the right side is always greater than 5. Whereas number 2 is always less than 5. So it's gonna be wise for you to eliminate all of elements on the right side. And the left hand side is always guaranteed to include number 2 or your searching number. Therefore, if the middle number or middle starting point greater than your target, you're gonna cross out the right hand side as well as the middle. And the middle is number 5. And we already proved that number 5 is greater than 2, which means it's different from 2. So you don't have to check it again, so you also cross it out as well. So now, let's assume your target is gonna be 9. You wanna search for number 9. And since 5 is less than 9, and also due to the increasing order nature, everything on the left hand of number 5 always less than 5, and it doesn't make any sense for you to have number 9 on the left hand side. And the right hand side always guaranteed to have number 9 because everything on the right hand is always greater than 5. Therefore, you're gonna eliminate the left hand side. And because we already proved that like 5 is less than 9 right here, it's not equal to 9. Therefore, you also cross out number 5 as well, so you don't have to check it again. Therefore, if mid less than target, you're gonna cross out the left hand side and the middle number. And what happens if your target equal to number 5? Then at the beginning, the middle starting point is also equal to your target. Therefore, you're gonna just return the position. And since the position of number 5 is at the 4th, so this is gonna be your answer. Okay, so I hope you understand these algorithms right here. And now let's solve the real problems. So now, let's say your target gonna be number 2. Again, at the beginning, you're gonna find the middle starting point, which is number 5. And now, you're gonna compare number 5, which is your middle starting point, with your target, which is 2. So 5 is greater than 2. So the algorithm said that cross out the right side and the mid number. I cross out the right side and the mid number. And it's gonna look like this. So now, your list has been shortened into the list of 4 elements 1, 2, 3, 4. Now we perform the same algorithms. At the beginning, you're gonna find the middle starting point, and in this case, it's gonna be either 2 or 3. So I'm gonna pick number 3. And also, if you pick number 2 as your middle starting point, then you go to this case right here and you just return the position. But we're gonna pick number 3 so you can have more chance to practice the binary search. So let's say the middle starting point is number 3. So you're gonna compare 3 with 2, which is greater than 2. So you're gonna follow this first if statement. So you're gonna cross out the right side and the middle number again. So right side and the middle number. And it's gonna look like this. I cross out number 3 and number 4. So now your list become the list of 2 elements only. And let's find the new middle starting point, which is either 1 or 2. So I'm gonna pick number 2. And since number 2 equal to the target, 2 equal to 2. So you just return position. And in this case, it's gonna be the first position. So that's gonna be your answer. But now, what happens if you pick your middle starting point at number 1? We're gonna perform the algorithms again. So 1 is less than 2. So this time you're gonna run this second if statement. If 1 less than the target, and which is true right here, you're gonna cross out the left side and the middle side. So because there's no left side, so you don't have to cross it, and you cross out the middle, which is number 1 in this case. And now your list of 10 elements at the beginning has been shortened into the list of 1 single element. And this is also the middle starting point as well. Since it's equal to the target, so this is your answer. And you're gonna return the position, which is the first position. So let's have another example. And this time we try to find number 9, which is right here. So at the beginning, you're gonna pick the new middle starting point. And from the last times, we re-picked number 5. So this time, let's try number 6. So you're gonna compare number 6 with the target, which is number 9. So 6 gonna less than 9. Therefore, you're gonna run the second if statement. You're gonna cross out the left side and the middle number. So I'm gonna cross out the left side and the middle number. So now you have a new list of 4 elements, and then you have to find a new middle starting point. So I'm gonna pick number 8 this time. So compare number 8 with 9. So 8 is less than 9. So you're gonna perform this if again. So you're gonna cross out the left side and the mid number. And cross out the left side and the mid number. So your list become the list of 2 elements, and you're gonna pick the new middle starting point. You can pick either 9 or 10. So I'm gonna pick number 9, which is equal to the target. So you're gonna stop the program and you're gonna return the position, which is the 8th position. But what happened if your middle starting point gonna be number 10? So you're gonna compare 9 with 10, so 10 is greater than 9. So you're gonna go to this first case. You're gonna cross out the right side and the middle number. There's no right side on number 10, so you don't have to cross it out. And you just eliminate the middle starting point only, which is number 10. So I'm gonna cross it out. And so this is the result after you cross out number 10 and you only have 1 single element left, and it's turned out to be your target, which is number 9. And you're gonna return the position, which is the 8. So after going through 2 binary search problems, now let's ask ourselves this question. What is the runtime of the binary search, and what makes it so quick and fast compared to the linear search? So in order to find the runtime, let's have another example. So this time, we're gonna target number 3 instead. And I also want to keep tracking of the mathematical expression of the binary search. So at the beginning, you have your list of elements, and I just say n right here to represent the length of this list. So we always start with finding the middle starting point, and it's either 5 or 6, so I'm gonna pick 5 this time. And when you find the middle starting point, you kind of like divide the list into 2 halves of equal size. You see 5 elements right here and 5 elements right here. So we're gonna have the left half and the right half. They both have equal elements. So now let's perform the algorithms. So your middle gonna be 5, and 5 is greater than the target, which is 3. So you're gonna cross out the right side and the middle number. So I'm gonna cross it out, and you can see half of the array has been crossed out due to the algorithms. And this is just an extra crossout from the middle. But this extra crossout doesn't deny the fact that like your array has been shortened from n into n over 2. So therefore, let's express it into the mathematical form. You just time it with 1 over 2. So this means you divide your list by half. So now you have the new list of 4 elements, 1, 2, 3, 4. And let's find the new middle starting point. And I'm gonna pick number 2 this time. So perform the algorithms again. 2 is less than 3. So according to this statement, when the middle less than the target, you're gonna cross out the left side and the middle starting point. So I'm gonna cross out the left side and the middle starting point. So it's gonna look like this. And as you see, originally this was the list of 4 elements, and now it become the list of 2 elements. It's like you drop from 4 to 2. So it's like another divide by half. So let's updating our mathematical expression. You just time put another 1/2 to represent that you divide the list of 4 elements into the list of 2 elements. Now your list is become the list of 2 elements, which is 3 and 4. Again, you find a new starting point, which is number 4, and 4 is greater than 3, so you're gonna cross out the right side and the middle number. So the right side will recross, so we just cross out number 4 only. And this is how it looks like after I crossing number 4 out. And also don't forget to update your mathematical expression, which is another 1/2. So now your list of n has been shortened into the list of 1 single element. So that's why let's set this formula into 1. So you can see from n element, I drop into 1 single element. So how this relate to the runtime? And you can see from n element, when it's dropped to 1 single element and 1 single element also your answer. And you can see right here, number 3, single element matching the target. So the 1 right here is actually your answer. Therefore, the runtime depends on the number of division or the number of time that you divide the n element list into the 1 element list. And for analogy, it's just like Thanos in Marvel Infinity War. So this is equal to like the number of time you snap your finger until your elements drop from n into 1. So every time you snap your finger, you drop the population by half, by half, by half. So just like Thanos, as you can see. So the runtime gonna equal to the number of times that the list gets divided by half until it has 1 single element, or the number of times you snap your finger until there's 1 hero left. So now let's assume n is bigger, like n kind of like goes to infinity. So you don't know how many times it's gonna be divided by half. So I'm gonna write in this thing in more general form. And this time we're gonna call the number of division equal to the runtime, because we already agreed that like the runtime depends on the number of times that the list get divided by half. So let's simplify this mathematical expression right here. You're gonna have n over 2 power runtime equal to 1. And from that, you can find that runtime equal to log 2n. And this is your runtime for the binary search. And as n goes to infinity, no matter what base you have, like log 2, log 3, log 4, they all converge to log n. So your final big O runtime gonna be O log n. So the runtime equal to O log n, which is less than the On of the linear search. Therefore, the binary search performs faster than the linear search. This is a summary of the binary search algorithms, and this is going to be the pseudocode that we have done on the previous slide. The first step, we find the middle number in the list, and then you're going to compare with your target. If your value like less than the target, you're going to repeat the same procedure but on the right half of the list. So just like you cut the left half and the middle and you only focus on the right half. If the target less than the value, you're going to repeat the same thing for the left half of the list. And if they equal, you just return the position of the value or the middle number. And we already proved that the runtime gonna be O log n. So in general, linear versus binary search, which one is better? It turned out that the binary search is faster than the linear search, which is log n compared to n. However, when you do binary search, you need to sort the array, otherwise it doesn't work. And when you sort an array, it's actually another problem in computer science, and that is gonna be on the sort algorithms videos. So stay tuned. And here is the data that show the performance between linear and binary. And you can see when your data is 10 million, it takes linear search 10 million times to execute, but for binary, it's only 24 times. And assume the unit gonna be years. So in linear search, it takes 10 million years to searching some data, but for binary, it's only 24 years. Linear search takes forever and it has high potential to crash your computer. So binary search make a huge performance and improvement in the searching problems. So I hope this video give you some basic understanding of searching algorithms, also reviewing some runtime analysis. Okay, so I'm gonna see you on my next video, which is the sort algorithms. Thank you.